Okay. All right. Hey, everyone. Welcome to the Control Machine Learning Seminar. It's my great pleasure to introduce Professor Yisong as our speaker today. So Dr. Yisong is a professor of computing and mathematical sciences at Caltech. He was previously a research scientist at Disney Research. Before that, he was a postdoctoral researcher in the machine learning department and the iLab at Carnegie Mellon University. He received a PhD from Cornell University and a Bachelor of Science from the University of Illinois at Urbana-Champaign. Yisong's research interests are centered around machine learning, and in particular, getting theory to work in practice. To that end, his research agenda spans both fundamental and applied pursuits. In the past, his research has been applied to the information retrieval, recommender systems, test classification, learning from rich user interfaces, analyzing implicit human feedbacks, data-driven animation, behavior analysis, sport analytics, experimental design for science, protein engineering, program synthesis, learning accelerated optimization, robotics, and adaptive planning and allocation problems. Okay, Yisong, thanks again for coming, and the floor is yours.
Thanks, Guanya. Thanks for the invitation. It's a pleasure to be here today. Today, I'll be talking about some of the work that my group and our collaborators have been working on, mostly at Caltech, in the area of learning for safety critical control in dynamical systems. Just to set the stage, of course, this is probably familiar to most of the audience, but to make sure we're all on the same stage. This is a talk primarily about policy or controller learning. And in machine learning, that's typically thought of as a form of reinforcement or imitation learning. And so how it works is that you have an agent that's interacting with an environment or a world, and the world has dynamics. And so the agent receives or observes some state or context from the world. The agent takes an action. The world, through its dynamics and the action, updates its state and passes a new state to the agent. And this process continues. And so the goal in the setting is to find some notion of an optimal policy. In imitation learning, that optimality is defined as minimizing some kind of imitation loss with respect to demonstrations provided by some kind of expert. In reinforcement learning, the environment itself is endowed with a reward function that you also observe, and the agent's goal is to optimize the cumulative reward that it receives along with the states. You can think of this as a learning-based approach for sequential decision-making. And of course, there are non-learning-based approaches too that have arisen in control and planning. If you're interested more in imitation learning, which is a little bit less studied than reinforcement learning, I invite you to check out this tutorial that I taught with my former PhD student, Huang. This was taught at ICML 2018. We take a broad survey over imitation learning approaches, as well as cover the fundamentals. So there are many exciting success stories in policy learning, ranging from board games to video games to protein folding. And perhaps one interesting commercialized example is the Microsoft Azure Personalizer, which is what's known as a contextual bandits algorithm that is used to help small businesses personalize their recommendation systems on their websites. And this is actually commercially deployed. But as we think of applying these approaches that have seen many successful, exciting success stories to the real world, other factors come into play, such as safety. And so I just want to share with you a quote. And this quote was said by an aerospace director of engineering, when he visited Caltech about 5 or 6 years ago. And he said, "Yisong, I want to use deep learning to optimize the design, manufacturing, and operation of our aircrafts. But I need some guarantees." So what are the kind of guarantees that the aerospace industry needs? Well, perhaps the most fundamental one is called stability. It's a control theoretic notion of a guarantee. And it basically says that any disturbance that takes my system off its desired path, I have a way of controlling the system so that it converges back onto the desired path, or in this particular simple example, a desired point. There's also safety, which says that there exists a performance envelope, also known as a safe set, and I can guarantee that my system will never leave this performance envelope. And what you see in this picture is that as the system starts to approach the boundary of the safe set, my controller understands how to act on the system to push it away from the boundary. And then there are simpler special cases such as smoothness, where I want to guarantee under certain assumptions that the system will never behave in a way that's too unsmooth, which could be undesirable for reasons such as comfort. Now, there are possibly other behavior guarantees that we might care about, such as fairness, low risk, temporal logic constraints, etc. And the mathematical frameworks I'll be describing today, at least in principle, could be used to think about how to incorporate other forms of behavioral guarantees as well. But since most of our collaborations thus far has been in the context of dynamical systems, we'll basically focus on the three types of guarantees shown below: stability, safety, and smoothness. Okay, so in thinking about this type of project, of course, we want to do research. And so the types of research questions that sort of underlie the collaborations and the applications are questions such as how to constrain learning to provably satisfy these types of behavioral guarantees. How does one integrate domain knowledge from physics and control theory, possibly towards a more unified framework that blends learning theory and control theory? And how do we exploit the resulting structure from this domain knowledge used to constrain learning to design learning algorithms that perhaps gives us provably faster learning? And faster here can be both computational and statistical. So you learn with fewer iterations and you learn with fewer data points. Okay, so in this talk, I will describe ways of integrating learning and control at varying levels of the system design. First, I'll talk about how to integrate learning and control at the level of the control action or the control output. Then I'll talk about ways of integrating learning and control at the level of the dynamics modeling, so modeling the transition function of the environment. And finally, very briefly, I'll talk about integrating learning into the optimizer of a very well-specified model-based planner that can, if you can solve the optimization problem, can guarantee safety. So let's start with the first one. So here's our starting point. We're going to start with our standard imitation learning or reinforcement learning, policy learning objective. So at this point, we're going to leave this aspect of it fairly generic. So we're minimizing some loss function of the environment or demonstration imitation loss. And that's what this argument of L of H is, where H is our controller. The thing I want to think about here is, given that we know how to solve the first argument, unconstrained, how do we add in these constraints? And so I'll generically just write the constraints like this, which means that if some quantitative measure of the controller is below some threshold, then some constraint that we care about, behavioral constraint, is satisfied, such as stability, safety, or smoothness. Now, this is not the only way to encode these constraints, but this is just the starting point that we'll use. Now, the problem here is that in general, this is very hard to verify or optimize because you need to, at least in the general case, you need to show that your controller, which could be a deep neural network, is provably stable under, let's say, a Lyapunov stability notion of stable for all inputs to the controller. And so naively, this is just very hard to verify, let alone optimize. And so the next step that we'll take in this logical thinking is to use a notion called functional regularization to a certified controller. What that means is that suppose that a domain expert, in this case, typically a control engineer, handed to us a class of model-based controllers that are certified by construction. So I'll use that to denote that by G. And so G, every controller in G, capital G, is certified by construction to be stable or safe or smooth, or et cetera. And the goal then is to train a policy H, which could be a neural net, to minimize some primary objective, such that its input-output behavior is close to some little g, some model-based controller within the class capital G. And the key idea here is that this class capital G encodes all the domain knowledge we're going to use from control theory into its design. And so we are asking the domain expert to give us a little bit more than just normal deep reinforcement learning, let's say. But in most applications, this is typically not that hard. And furthermore, because all the controllers in G are suboptimal, they're typically not optimal, then we can do better in the primary objective than any control in little g while still retaining guarantees. And of course, we could rewrite this in a Lagrangian form rather than a constrained form. Now, although I've added this extra piece, in some sense, naively, this still looks intractable because I have to verify that G is close to H for all inputs to G and H. It turns out that for many classes of behavioral guarantees, the formulation I just presented you in the previous slide actually has a closed form solution. And the solution looks like this. So this is a new solution concept. It basically learns a residual action behavior on top of the behavior of a model-based controller. And so the basic idea is as follows. So our policy class H is explicitly represented by a tuple F and G, where F is a neural net, let's say, and G is a model-based controller with certifiable guarantees. And so at runtime, given an input state S, the policy predicts an action that minimizes a trade-off between the neural net's prediction and the model-based controller's prediction. And if you capture the trade-off using squared distance, then this has a closed form formula at the bottom, where basically, if let's say the lambda tuning parameter at the bottom is something like 10, which is about what it is in many of our experiments, then the model-based controller is doing most of the work. And the neural net is basically predicting a behavior, a residual behavior to sort of steer the model-based controller's prediction a little bit to offset its behavior. And that's basically what's happening. So we're learning a residual behavior on top of what a model-based controller gives us. Now, what are some theoretical guarantees? And this is just a high-level summary. So it turns out that by construction, any H we learn in this kind of space is close to G, to some G. So this is a form of regularization. In particular, if you have certifications on G, such as stability guarantees, it turns out that you can prove that H has a relaxation of that certificate. So approximate stability, or approximate smoothness, or approximate safety. This approach is compatible with conventional imitation learning and reinforcement learning approaches because we didn't really touch that primary objective at all. We just abstracted it, so you can solve that using any using imitation learning and reinforcement learning approach. So this is a modular framework. And furthermore, if you choose to exploit the structure of G, and so of course, you can just pretend that capital G encodes all your domain knowledge, and then you don't have to think about it if you're a reinforcement learning person. But if you choose to exploit some of the structure in G, then you can actually design new learning approaches with faster convergence guarantees. And this is very data efficient, so we'll show later that at least in the reinforcement learning setting, this leads to very low variance gradient estimates, which leads to much faster learning. So I want to sort of take a second to talk about this regularization idea that I touched on in the first bullet point in the previous slide. So this indeed is a notion of regularization, and you can see this in the following way. Suppose that we make the assumption that we were working with a class of neural nets, capital F, that are so expressive that they can model, at least approximately, the input-output behavior of any other function, including any other G. So what that means is that any input-output function in capital G, so any little g, can be approximated by any neural net in capital F, by some neural net in capital F. And so G is a subclass of F in a functional input-output sense. And H then is also, therefore, a subset of F in a functional input-output sense. And so this is indeed a form of constraint or regularization. And here we're regularizing not in the parameters of the neural net, we're regularizing its input-output behavior. And we're regularizing it such that we want to learn a neural net whose input-output behavior is similar to the input-output behavior of some G in our class of certified controllers, capital G. So in this sense, this is a form of regularization. It's interesting because this is a form of test time regularization, because we don't actually have to solve the optimization problem imposed by this regularizer at training time, like many regularizations. Because little g is with us at test time, we actually get this regularization with us for free, as long as we can select a little g from capital G. So some comments on optimization. So the primary way that we think about optimizing this approach is through a framework of alternating optimization. So first you pick a G. So again, a domain expert may have to help you here. You hold G fixed and you optimize F, the neural net. And then you hold F fixed and you optimize G. You pick a better G from your class capital G. Each of these steps reduces the quote unquote standard approaches. The first one reduces to any imitation learning or reinforcement learning approach that you would like to use. If you're interested for a clean treatment of this idea framed as a form of constrained mirror descent, I invite you to check out our NeurIPS 2019 paper, which studied it from this perspective. One could also consider a fully differentiable version rather than doing alternating optimization, just a comment. Okay, so let's talk about some applications. So this line of research was started by thinking about this particular application, which I started thinking about when I was a research scientist at Disney Research. Disney owns ESPN, and so there's an interest in doing automated broadcasting and sports analytics more generally. In this particular application, the idea is as follows. We are collecting tracking data of the locations of the players on the court. We're also collecting data of how a human broadcast operator is directing a broadcast camera, where to point the camera to compose footage for home consumption. The goal then is to train an autonomous policy for how to point the broadcast camera from this training data. So this is an imitation learning problem, such that we can implement this on a robotic camera and automate the broadcasting part. So the naive approach that our collaborators first tried, and it's a very natural approach to try first, is to do a straight up supervised learning approach where you train a predictor per frame. So given where the players are on the court, where does one point the camera? So it's a regression problem. And you get a result that looks like this, where X is the time axis and the Y axis is the panning angle of the camera, so the horizontal angle. The black line is the human demonstration and the red line is the predictor. And it's in a squared law sense, it's pretty accurate, but you'll notice that it is very jagged. And so you actually would not want to watch footage from the red line. It would give you a headache probably. And so in practice, what people do in this field is they do some sort of two-step smoothing where they have a smoother that they know is smooth, typically provably smooth, and they just do a post hoc smoothing on the neural net's prediction. Of course, the smoother is ignorant of the context, which is where the players are on the court. And so it ignores that context, so it over smooths at places. And so you're trading off smoothness for accuracy. And so through this collaboration, we developed the first instance of this smooth policy class solution concept, where now capital G is a class of provably smooth models. And this is very easy to design. In fact, in our case, the capital G is just a class of constrained linear autoregressors on the previous actions of the camera. And it's easy to prove that is provably smooth. And then F is some complex function class like neural nets or random forests, etc. And again, you get this same idea of test time functional regularization, where you're training a policy H that you can prove is approximately smooth. And you get a result that looks like this. So again, X is the time, the Y axis is the camera angle, blue here is the ground truth human expert, and red is our prediction. And you can see that this is both accurate and smooth. And we got this result using only 30 minutes of training data from a live game. You can superimpose the predictions on top of the original game footage to get a sense for how the composed video might look like. And so here's a comparison. On the right is our approach. On the left is the two-step baseline. And I should also mention that you can implement what you see on the right on our autonomous robotic broadcast camera right now. One fun fact about this project was that I believe this was the first time that a machine learning project was covered on Sports Illustrated, excuse me. Okay, moving on. So now let's talk about how to use this solution concept for more advanced notions of behavior guarantees, such as stability. And so this is referred to sometimes at Caltech as control regularization. So the basic solution concept is the same. F is a black box predictor, G is a model-based controller, but now G has control theoretic guarantees such as stability. And F we can learn using any deep learning approach. And so again, you can show that if G has some sort of stability guarantee, like a Lyapunov stability guarantee, then H, this neural net plus model-based controller, also has a relaxation of this stability guarantee. If you're interested in the details, you can check out this paper, which was published at ICML 2019. Furthermore, you can show that the variance of the policy gradient, so you train F using policy gradient or some form of reinforcement learning approach, and you could show that the variance decreases by a huge constant factor when training using this approach, which leads to much, much faster learning. And so here's just one comparison. So the right-hand side is a zoom-in version of the left-hand side. And the baseline RL method that we compared against is DDPG in red. And you can see that the variance is huge. And the other lines are different versions of our approach. And so here's just an example on the Torx car racing simulator. So on the left is our approach. On the right is the normal DDPG. Which crashes very often, early and often when it starts learning. And our approach can learn to very efficiently complete a lap very quickly. Okay, so to summarize, what I presented in this first part of the talk is a notion of functional regularization that's designed to blend learning and control in the action space. And you can frame this as a constrained or regularized learning framework. And at least for a special class of these problems, we have this solution concept at the bottom. And basically, the idea is that you use control methods. You work with a domain expert to design a family of control methods with analytical behavior guarantees. So everything in this, every controller in this class of controllers is certified by construction. You blend this with learning in the action space to improve the precision or the flexibility of your overall controller, which leads to more optimal behavior in the real world applications. If you do this, at least in some cases, you get to preserve these side guarantees, possibly a relaxed version of these guarantees. So in some sense, what I've shown you today is one of the first instances of a deep learning-based controller with a Lyapunov stability guarantee. You can interpret this as a form of regularization, which you can leverage to speed up learning, because regularization can be used to leverage to speed up learning, both in terms of computation and in terms of data efficiency. And of course, there are other directions, such as offline learning and blending with controllers with logical constraints rather than dynamics constraints. I'll pause here briefly if there's a quick question about the first part of the talk.
If you have a question, you can actually unmute yourself and directly interact with Yisong for this part.
Okay, I can move on. We'll have time for questions at the end as well. Okay, so the next part of the talk is about how to integrate learning and control at the dynamics modeling level rather than the action level. And so we'll be working with model-based control then, of course. And so this is just a generic way of thinking about model-based control. You have your current state, ST. You have your action, which I'll denote as UT here. And then you have your model of the dynamics, which gives you their next action given the current state and the current action, plus some unmodeled disturbance or error or noise. And so, robust and optimal control and other methods of control, to a first order approximation. Of course, I understand that I'm oversimplifying things if you come from a control background. To a first order approximation, you can think of optimal control and robust control as a form of very fancy contraction mapping that has these convergence guarantees through the contraction, such as a Lyapunov stability guarantee. The precision or the optimality of what you converge to depends on the error epsilon. So if your error is very huge, then you may only converge to sort of a very sort of big space that you cannot converge any further with higher precision. If epsilon is very small, then you could sometimes converge to exactly the point that you care about. So the idea here is we're going to think about how to learn residual dynamics. So F tilde, you could think of as implemented using a neural net, and the normal F is given to you by the domain expert. And the hope is that if we learn this F tilde using, let's say, deep learning, then the residual error, the epsilon, is going to be much smaller than before. And so if we do this in the right way, then we can again leverage all the tools that we have in control theory, and we can perhaps even preserve our stability guarantees even if we use deep learning. This does require some constraints on F tilde, such as F tilde being Lipschitz and having bounded error. But otherwise, once we satisfy those constraints, then we could sort of just plug this into a standard control workflow. And so this is motivated by an application in drone landing. And so in drone landing, the way you think about it is you have a drone where you have the good nominal aerodynamics model of the drone. But when the drone lands, it's interacting with a boundary condition. And this boundary condition then perturbs the nominal aerodynamics model. And it's really hard to capture this using first principles. And so what we're going to do is going to learn the residual effects of the ground, this boundary condition, and plug it into the standard aerodynamics model of a drone. And so this is a very simplified form of a control system formulation of a drone. It's very standard. And the point is just to look at the FA and the tau A on the right-hand side, because that is implemented using neural nets. And everything else is standard. That's the entire point of this slide. And so this is what data collection looks like. We fly the drone. In this case, we flew it manually for about 6 minutes. And we flew close to the ground at different speeds. And we collected the residual error of what our nominal aerodynamics models predicted versus what actually happened. And then we used that to train this residual dynamics model F tilde. That's the basic idea. And then we implemented F tilde using a spectral normalized neural net. And the reason why we use spectral normalization is that it ensures by construction that F tilde has a Lipschitz constant. And so here's some of the prediction results. So the green dots are the actual measurements in the lab. The orange lines are various predictions made by physical models that people try to derive using first principles. And the blue line is the prediction of our neural net on the residual error of the ground effect. And you can see that the error is extremely small. So this was able to learn very accurately. Another thing that's important is that we can generalize. So on what you see here is a plot of the predictions. On the x-axis is the velocity. So we can We can be going up at 1 meters per second, and we could be landing at up to 2 meters per second in this example. And then the y-axis is the height from the ground. And the training set was only collected in this case when landing up to 1 meters per second. And you can see on the left, that the spectral normalized neural net is able to generalize its predictions to new domains where you're trying to reason about what would happen to the dynamics if you were to land even faster. And so the controller design is very simple in this case, actually. It's just a feedback linearized PD control. I don't want to go into the details too much, but the basic idea is that using this residual dynamics, you can cancel out the ground effect. And then because it's a feedback linearized control, you can just do that in the control space. The way we do this does require that there's a Lipschitz constant and a small time delay on our controller, which are satisfied in the robotics application. And then you get a stability guarantee like as follows, where this basically says that we are converging exponentially fast to a tube or a small sphere or ball, and the radius of this ball depends on epsilon, which is your residual unmodeled disturbance. So the smaller epsilon is, the more precise you can control this drone. The bigger epsilon is, the less precise you can control this drone. And the basic idea is that we want to train a neural net to estimate the residual dynamics such that epsilon is as small as possible. And so once you do that, you can just plug it into a standard control theoretic analysis like this one to get this kind of guarantee. And so here's just an example. In this example, the drone is flying with high precision, very close to the ground. And this is almost impossible to achieve this level of precision flying close to a boundary effect like the ground with conventional controllers without using learning with this type of hardware. Now, the ground is a boundary condition. It turns out that other drones around you are also boundary conditions. They're sometimes mobile boundary conditions, and they act on you in terms of the downwash. So one drone flying on top of another drone can also push air down on the drone below it and destabilize the drone. So you can think of neighboring drones as also moving boundary conditions. And you could extend this idea to model not just the ground effect, but also other drones around you and do high precision, dense formation flying on consumer drone hardware. Okay, so as an aside, one thing that I mentioned briefly in the previous slides is that we initially collected data sort of using manually designed trajectories to collect data. If you want to be able to collect data fully automatically, then you need to use ideas from an area of research called safe exploration, where the robotic system can automatically design what trajectories to fly to collect more data to be able to build a better dynamics model. But it must do so while guaranteeing its own safety. And so we've also been working in this space. And so my postdoc, Angie, designed an approach called robust regression, which uses deep learning and can be used for a limited amount of provable extrapolation, which you can use for safe exploration. And so robust regression actually gives you a guarantee on the error. So if you have a Lipschitz constant on the dynamics model, so you have your unknown dynamics model, you can upper bound it with a Lipschitz constant. So it's never changing that quickly as a function of state. And then with robust regression, you can actually prove that you can generalize a little bit beyond your training set. So if you collect the data up to landing at 1 meters per second, you can prove that, for instance, you can generalize with relatively low error to landing at up to 2 meters per second, just as an example. And from that, you can integrate this with trajectory design and to design trajectories to collect data that's informative for improving your model to be able to extrapolate even further while guaranteeing safety as well. And that's the basic idea. And if you're interested in details, this idea was published in 2 papers listed below. As another aside, you can also do learning not just in the full residual dynamics or the full dimensional dynamic space, but also in projections of the dynamic space. So in particular, for many high dimensional systems, such as a bipedal robot, which can have up to 60 or 100 degrees of freedom, you typically don't want to learn the full dynamics of the system because it's just way too high dimensional. And so there are ideas that people have studied in control that try to model projections of these dynamics that are relevant for certain actions you may want to take. And in the context of collaborations here at Caltech, this is encoded in learning control Lyapunov and control barrier functions, which encode these low dimensional projections of the dynamics. In particular, for control Lyapunov functions and control barrier functions, the degrees of freedom is with respect to the action space rather than the state space. So you may have only a low degree of freedom in terms of your actions, such as maybe like just 10 or so, and your full state space could be 100. And so this can be easier to learn than the full dimensional dynamics. And so how does one actually estimate this projection, learn a residual function in this projection of the dynamics? And so we've done some work studying this as well. So to summarize, in this part, we talked about how to learn residual dynamics for model-based control. We show that if you can learn this residual, sorry, the gardener. We talked about how if you can learn this residual model in a way that can control for the Lipschitz constant of the neural net, then it basically gives you a compatible mathematical structure to just plug this in to standard control workflows. So you can use standard controller design, inherit their stability guarantees. And if you want to do safe exploration where you automatically collect this data, then we also have been doing some work in that space as well. So I think I'll just move right along to talk about the last part, which is integration in the optimization problem. And so now we're doing model-based planning. So we assume that we have a very good model of the environment. And the goal is to design a trajectory. So design a global plan, if you will, within some horizon of planning. And we want to, of course, satisfy safety constraints. So the previous topics that we've studied in this talk, they only satisfy local constraints. So stability is a very local guarantee. And you prove stability over time by proving a Ford invariant. But if you want to actually have a global guarantee, like that it doesn't reduce to a local guarantee, then you require different approaches. In general, this is an NP-hard optimization problem, so it's very hard. And so we've been thinking in our lab in an area called learning to optimize. So the idea is you view optimization as a sequential decision-making problem. So for instance, many solvers that we use in practice are sequential in nature and how they work. Tree search, the greedy algorithm, gradient descent, these are all sequential decision-making procedures. So you can view this solver as an agent or a policy. The environment that this agent is interacting in is the search space of this optimization problem. So a state is a representation of where you are in the search space, like an intermediate solution. And the goal is to find a state with high reward, which is a good solution or an optimal solution or a feasible solution to this optimization problem. And so we want to basically use learning to do this, to do better local decision-making to navigate a search space that if we can navigate well, gives us global trajectories for the actual outside robotic system. And so we've studied this idea in a few different contexts, such as learning to search or learning to plan, learning for submodular maximization, which can also be applied to things like experiment design, like protein engineering, and learning to infer, where if you have a continuous optimization problem, like often arises in deep generative models with variational inference, how do you actually speed that up? In the interest of time, I'll just give you a few highlights from the first section on learning to search and learning to plan. And so here's the basic idea. We have some distribution of planning problems. For instance, obstacle courses on the surface of Mars that we've sort of collected data and mapped out. We compile that to some sort of constrained search problem where we want to find optimal paths that guarantee safety over the entire path. We collect demonstrations offline from an external solver. For instance, if this is compiled as an integer program, we could use Cplex or Gurubi. The solver is too slow to run at deployment time, but it's fast enough to use to collect data offline. We use imitation learning to imitate the behaviors of the expert to be able to learn good policies. And this imitation learning algorithm is then much faster to run. And then we deploy it on test instances at deployment time, where this obstacle course is then drawn from the same distribution as the training set. That's the basic idea. I won't go into the details. Here's just one result for obstacle path planning with risk constraints. And so lower is better. Our approach is in blue, and standard integer program solvers are the other two lines in red and green. And the basic idea is that we can indeed do better than off-the-shelf solvers. One ongoing project is to integrate this with the navigation module used in the Mars rovers. So this is a collaboration with JPL. And so the Mars rover needs to do a lot of path planning. The basic mission of the Mars rovers is to do science, but the Mars rover actually spends a lot of time getting from point A to point B to do the science. And the faster that we can do planning, the more aggressive that we can do planning, then the more science we can do. So that's the basic idea. One of the biggest bottlenecks in safe path planning on the rovers is the fact that figuring out which branches of the search space to use for path planning to prioritize is actually very hard to do. And if we can use learning to basically prune away parts of the search space that we know are suboptimal, then that would dramatically speed up the rover. And so we can, of course, implement this in high fidelity simulators that is used in the production workflow for the design of the rover's planning module. So this is sort of a visualization of what this high fidelity simulator looks like. The physics of this simulator in terms of the, navigating the obstacle course are very high fidelity. Okay, and so here's just some preliminary results. I want to direct your attention to the bottom right corner of these plots. So smaller numbers are better. Basically, the right-hand side are obstacle courses that are harder. So they have a higher density of obstacles. And so these numbers basically correspond to the amount of time the planning software spent finding paths. And so you can see that using machine learning on the right, the numbers are much lower than on the left. In some cases, less than half of the search time. Okay, just another example. We can do this not only for planning a single agent, we can also do this for planning a swarm of agents in a decentralized way. So the basic idea is that you have, again, this distribution of obstacle courses and planning problems. You can offline run a global planner that computes an optimal solution, use that for decentralized imitation learning, and then implement this very quickly and very efficiently on localized agents. So here's an example. We have 6 drones doing very fast, decentralized, and provably safe planning. And I want to mention that the neural net is actually implemented on these drones, and they're running at about 150 hertz. So this is a very low power solution. Okay, so just to summarize, we've looked at ways of blending model-based methods and control methods with learning in the action space. In the dynamic space, looked at how to use learning to accelerate hard optimization problems for a model-based planner. Maybe a fourth concept to fill this quadrant is how to use integrate model-based components into a more sort of holistic learning-based viewpoint. And this is, of course, a topic for further research. Finally, I'd like to thank my collaborators. So most of this work was done by students and postdocs in the top row. And so without them, of course, none of this would get done. And if you're interested in the references, here's a list, and I'm happy to take questions. Thank you for your attention.
Okay, thank you, Yisong. If you have a question, feel free to mute yourself. And actually, we have a question from the live stream audience, and it's very interesting, a high-level question. Yisong, could you comment on some trade-offs if you integrate physical models or like control actions from control theory to learning compared to the fully model-free learning method?
Absolutely. Let me, I think that's best described. That's a great question. Let's start with the action space one. And I think the trade-off is exactly, can be exactly expressed in this slide. So if you want, in this particular formulation, I guess I can't comment on the sort of the optimal trade-offs. I don't know what the optimal trade-off is, but for this particular solution, the trade-off is as follows. We can only learn something in H. We cannot learn something in F. So there could be something in F that is more optimal than what is in H. But if it's not in H, we cannot prove these behavioral guarantees like safety, stability, smoothness. And if you can't, and so if you violate those behavioral guarantees, then your controller may be useless in practice or not usable in practice. And so I tend to think of these trade-offs as multidimensional. So in reinforcement learning and imitation learning, one typically thinks of there being only a single objective function, which is your reward. In most real-life applications, there are many objective functions. Here, I'm just looking at two, right? Stability and reward, let's say, or smoothness and reward. In reality, there's actually many more than two, but here I'm just looking at two. And so navigating the Pareto frontier of that trade-off space is actually very challenging. And I think that you'll necessarily, if it's a high dimensional objective, like you have 10 objectives, then I think it's very hard to sort of navigate that efficiently without some sort of modeling assumptions. But once you add those modeling assumptions, it necessarily constrains your space, and you cannot do better than your constraints. So I would say the general idea I don't know how to answer. On a case-by-case basis, I think this type of picture gives you a clear idea of what the trade-offs are.
Thanks. That makes sense. Any other questions?
Oh, hi, Yisong. Yeah, I have a following up question on the same page. So I feel a very appealing property here. If you you have this guided policy G, you can inherit some good property from this G, like say stability or robustness, and this framework is pretty simple. We just regularize F, the distance between F and G. So is that kind of magic always true, or it's more like case by case and requires a lot of
no it's not always true. Let me spell out explicitly some of the requirements. Number one, the only guarantees you're looking at are local guarantees. So smoothness is a local guarantee. You can compute it based on the current time step you can compute it based on the states of the current time step and the previous time step. Stability is also a local guarantee. You can compute it based on the current, depending how you represent state, the states from the current time step and the previous time step. The way you get these proofs of stability is that you invoke this forward invariance. But the actual certification of stability starts with a local guarantee. So stability and smoothness are all local guarantees. And so if you actually just think about it for a second, if G has a proof that it's smooth or stable, that's a local guarantee. And what I'm saying here is that locally per time step, but that's a local in terms of time per time step. It's local in terms of time. So basically what this is saying here is that at every time step that I'm making a prediction, I am predicting an action that doesn't deviate too far from the action of G. So that approximately preserves this local behavioral constraint. And you could show that in certain cases that you can also invoke forward invariance like Lyapunov stability. So that's number one. Number two, in order to get this work in practice, of course, the time steps, the time discretization needs to be sufficiently small.
I see, thanks. And another question is on the second part on the control diagonal function and control barrier function part. Since you go over that, past that a bit quick, so could you give a bit more details on that? So what is the setup? Are you assuming the model is known and you just try to learn this certificates, or like what is the setup and how does that relate to the dimension reduction kind of? Yeah.
Sure. So it's the same. It's at a high level the same setup as learning a residual model. So what people do in these high dimensional systems, at least one thing that you can do, is you. So this requires going into a little bit of control theory. So if you have a control affine system, which means that the control action interacts with the state space in an affine way, in a linear way in some sense. Then you can actually design a Lyapunov certificate just on the control affine part. And so what that means is that the certificate, the degrees of freedom that you're analyzing the certificate is equal to the degrees of freedom of the action space. Most people, when they derive certificates or barrier certificates, it's over the full state space. But if you have a control affine function, you can actually design control barrier functions and control Lyapunov functions whose dimensionality is just the action space, because you're just looking at the control affine part. Now, if you have a nominal model of your control affine system, you can again learn a residual of the control affine system. And that's what we're doing here.
I see, got it. And you're like the residual is on the fx, where it also considered the HU.
It's just on the control affine part.
I see.
So f of x is the full dimensional state.
Mm.
Yeah, sorry, I don't have the math here, but yeah, it's just on the control affine part.
Got it. Thanks.
Hi, I have a question.
Yeah.
I want to ask what is the advantage of this approach compared to direct adaptive control if we consider a over-parameterized model?
Sure, there are a few advantages. First of all, adaptive control is, you can think of that as on-the-fly learning. These methods are all what I would call episodic learning. So that's a difference, and they have relative strengths and weaknesses. If you do on-the-fly learning, you have to, in some sense, make a different set of assumptions than if you're doing episodic learning. For instance, if you work on problems where you actually cannot adapt on the fly sufficiently, then adaptive control just doesn't apply. For instance, if you want to do high-speed drone landing, just to give it one example, if you want to do high-speed drone landing and agile control close to a ground, as far as I know, the way you want to do that is you fly a little bit slow, and then you train your neural net, and then you compute a new neural net residual model of the ground effect or any boundary conditions. Then you fly faster, collect that data, and then you train, and you collect more data. You fly even faster. So that's called episodic learning, and it's a very different way of doing learning than online or on-the-fly learning, which is effectively what adaptive control is. And so I think they're suitable for different situations. In this case, I have a hard time imagining that you can actually adapt on the fly in a single shot.
Thanks.
Okay, I have a question. So I guess for the whole talk, it seems like to be focusing on using this data-driven approach plus some control theory to do engineering. And I wonder if, I guess, there's a reverse logic of using all this math to understand, say, how animal behaves. For example, for a simple system of Drosophila, which is fruit fly flying, it's already a complicated system. For example, it needs to decide whether it's a predator to escape from or a safe place to land on, and it needs to do real-time decision making and also a lot of path planning. probably not online, but it needs to do a lot of complicated maneuvers depending on the scenarios. And I wonder if there's any, it's almost reversing this logic of using data-driven approach to engineer a system. But there, I guess, my personal interest will be understanding how, I guess, animals, what animals are doing when they're flying, for example. And I guess, what's your take on that?
Sure. So everything I've described here operates at a single level of control and decision making. So, for instance, some of these examples at the end operate at the level of planning, and then the examples I gave in the front operate at the level of basically instantaneous control. What animals, and indeed what very complicated robotic systems like the Mars rover do, is that they have a hierarchy of decision making. So the low level decision making is almost like reactive control or feedback control, and then the highest level decision making is like typically in a rover, it's you can think about specifying in terms of temporal logic based planning, right? And so you have this hierarchy of abstractions of models and hierarchies of timescales and hierarchies of decision making. So the first thing I would say is that for any animal, even a simple animal like a Drosophila, if you actually want to understand, quote unquote, what it's doing, you actually have to model the entire hierarchy. And everything I've done in this talk focuses on a single level in that hierarchy at a time. So it's a good question. I don't know how to answer that question yet right now. But yeah, if you want to jointly learn multiple levels of the hierarchy at the same time, I think it's a very interesting question. I think people are studying it. One area is called hierarchical reinforcement learning. But I think, if you actually want to use that to model, biological systems like Drosophila, I think there's still a lot of work that needs to be done.
Thanks.
Any other question? One quick question from the South Trick from the YouTube. How do you quantify smoothness from a given control policy?
Sure, great question. So the way you quantify smoothness, I don't think I have a formula here, but well, okay. So the state, so so mathematically, what the state encodes, this S, is not just where it encodes both first 0th order information, like where you are right now, but it also encodes first order and second order information. So you can think of that as saying what's actually in this state is where the camera was pointed at the previous time step, at 2 time steps ago, at 3 time steps ago, at 4 time steps ago. Okay, if the state includes all that information, then you can basically measure smoothness using like a sort of a discrete time derivative type of estimate the velocity. You could estimate the acceleration. You could estimate the change in acceleration or the change in velocity, and then you can basically say, look, I will never take an action that causes a change in velocity of more than some number, and that's how you ensure smoothness.
Can you explain what the so you mentioned that if G is stable or has some amount of stability constant, then your learned policy has some relaxed stability. Can you explain what more that relaxation means?
Yeah, so it just depends on lambda. So if lambda is 0, then I have no guarantees. If lambda is infinity, then I exactly preserve whatever guarantees are in G. Of course, I'm not able to learn anything outside of G. So if lambda is 10 or 100 or something, then you get sort of a relaxation that depends on how big lambda is. That's basically it.
I see. Thanks.
Okay, since we are a bit over time, do we have the last question? If we don't, yeah, we can just finish this seminar, I guess. Okay, seems nice. So thanks everyone for coming. The next week, we are going to have Professor Marco Povang from Stanford. See you the next week. And thanks again, Yisong, for coming. And thanks everyone for attending this seminar. See you the next week.
All right, thank you.